For our next presenter, we have Quan Lin Lee, who's going to be discussing advanced heat pipe reservoir variable conductance heat pipe with enhanced reliability. Yeah, why don't you introduce yourself and then take it away?
All right, thank you very much. So good morning, everyone. My name is Quan Lin Lee. I'm a lead engineer in the R&D department of Advanced Cooling Technology. My presentation today is also related to hard reservoir variable conductance heat pipe that Jeff Debo, my colleague, just presented. But my focus of research is about how to increase the reliability of this hard reservoir VCHP for future planetary landers and rover applications. And my VCHP is going to be an integrated versions compared to the one that Jeff presented as a non-integrated. And co-author for this presentation, including myself, Colleen Theroux, Bill Anderson, and also this is a STTR effort, so we do have a university partner. Case Western Reserve University is our collaborator for this program. Okay, so the good thing about after Jeff, because I don't need to talk about too much background about VCHP, but for future lunar applications, especially for 14-day night survival, we are looking for very reliable variable thermal links to connect between the payload and the heat rejection systems, so that we can shrink our radiator during the day and then minimize any power needed to survive for those to keep those payload temperature high. During a lunar night. You can use standard VCHP with a cold bias reservoir, as the figure shows here, which is very common for spacecraft application. But for this lunar night application survival, you need to provide 1 or 2 watts of heat to the reservoir to maintain your evaporator temperature within a 1 or 2 degree control capability. But the problem is, if you want to produce 1 watts of heat, you will add weight penalty, like the bullet point shows here. You will add approximately 5 kilograms of mass associated with battery or a solar panel for 14-day lunar night survival. So that's why ACT have been developing hot reservoir variable conductance heat pipe technology for this application. So the schematic shows here is kind of repeated, but it's integrated versions for the hot reservoir VCHP. You have basically taking heat directly from the payload to maintain your reservoir temperature. The benefit of this is you can have much tighter thermal control capability than the regular VCHP. And also this is going to be a passive because you're taking heat directly from the payload, so you can potentially eliminate any electric power needed for reservoir heating for 14-day lunar night. So it seems to be a very promising technology for these applications. However, in 2017, ACT tests VCHP, hard reservoir VCHP in ISS as a part of APTX experiment, and we found that the one of bottleneck for the hard reservoir VCHP is you have to have a very good fluid management strategy to avoid any working fluid going to the reservoir, because like Jeff explained, if you have working fluid or any vapor in presence in the reservoir, you will push the non-condensable gas out from the reservoir, and that will occupy the condenser of the heat pipe and significantly increase the delta T of the heat pipe. So we need to avoid that thing happen. If that happened, the only thing you can do is like you can heat up the reservoir, but this is the integrated version, so you are not able to heat it separately. The other way is just wait until the diffusion starts to take over and then redistribute the distribution of a vapor and NCG in the heat pipe, and they will take hours or even days to achieve. So under this STTR, we are developing a new features that can improve the fluid management's performance of the hard reservoir VCHP, especially for the integrated version. So in this is the concept we are developing under the phase 1, and right now the program is in phase 2, and we have a potential follow-on program. The idea is having adding another tube to connect them between the condenser and the reservoir, and forming a loop like that, like this schematic shows. And because of the loop configuration, you are able to use the momentum of the vapor, which is shown in the light yellow color in this cartoon. The vapor will have momentum, and that will drive the NCG flow to circulate through this loop. So we call that concept as a VCHP with NCG flow, and this flow will be able to remove or migrate any excessive moisture in the reservoir and purge your reservoir without using additional power. So we call it like a passive purging capability. And the analytical solution showing on the right show you how effective if you can introduce some flow in this VCHP. So compared to the diffusion-based purging, if you can generate like a 2 centimeter per second of flow, your purging time can reduce from 24 hours to less than 30 minutes. So it's like 100%, 100 times faster than the state-of-the-art. The concept was demonstrated successfully in phase 1 through analytical solution, numerical model, and also through the proof of concept prototype. And we confirmed that the flow exists, and with a proper design of the internal NCG tube, geometry, and length, we should be able to generate a good amount of flow for purging. More detail you can find in the conference paper we published in the last 2 years in the ICS conference. Today's presentation is going to be focusing on the prototype we developed in the recent time, and showing the reliability enhancement implementing this concept. So the figure shows on the left is the VCHP prototype we made. As you can see here, the reservoir and the evaporator are actually integrated as one pieces. In addition to that, we also integrated the external line with the heat pipe main body. So this is really a compact design. And you also can find that we have 2 field tube in this hardware. One field tube is at the end of condenser. This is considered to be a regular field tube for working fluid and NCG charging. The other field tube is on the top of reservoir. This is for reliability testing, which will be explained in the later slides. And in addition to temperature measurement, we also have the pressure transducer to monitor the pressure change during the testing. This pipe was made by aluminum 6061. It's pretty conductive, but you can also make with stainless steel or any kind of material that we use for the VCHP, hardware for VCHP. And this has a groove structure for liquid return, and the test setup is showing on the right. This was tested in a horizontal orientation with a slightly against gravity. 2 working fluid was used for testing. One is acetone, one is toluene, and we are planning to do an ammonia test in the incoming months. So before we talk about reliability testing, first let's take a look on the thermal control. The goal of this quick and dirty test is to make sure that after we implement the external line, the thermal control capability of the hardware of VCHP will still be there. So initially, at the on conditions, the VCHP was operated at 75 watts of heat input, and sink temperature is about 40 degrees C. And we start decreasing the sink from 40 degree all the way to minus 80. The evaporator temperature showing that this red line only drops about 20 degrees C, and then we start to decreasing the heating power to see what is the survival power. In the end, we decrease the power from 75 all the way to 2.5 watts, and steady state. I think the steady state evaporator temperature around minus 12 degrees C, and the sink temperature is minus 80. The on conductance is around 3.03 watts per K. The off conductance is 0.037. That's very watts per K. So it will result in a turn down ratio about 82. But this is made by aluminum, so the actual conduction is pretty high. So the takeaway message of this thermal control testing is that we can still have a pretty good turn down ratio after we introduce that additional external line for flow, for momentum-induced flow purging. Hey, so like I said, the goal of this program is to really understand the reliability enhancement after implement this concept. What we're trying to do is demonstrate that the new VCHP we developed here can quickly recover back from some abnormal situation that potentially happened in the real applications. There are two situations we are considering here. One is while the heat pipe is operating, what happens if we introduce some working fluid liquid directly into a reservoir, and then the heat pipe will definitely not operating for a while. How fast we can recover, how fast we can purge out those working fluid from reservoir. Second is we call it extremely conditions. We want to know whether this heat pipe able to start up if all the working fluid was initially charged in the reservoir and no fluid in the evaporator. Of course, this is not going to happen in the real situation. This is really a worst case scenario. But if we can successfully start up from this scenario, the heat pipe will be able to stop up in any situation. So the test was was performed in a sequence. First, we did a startup, regular startup, and then we introduce some fluid into a reservoir and see how fast you can purge. And then we recharge the fluid, but all the fluid was charged into the reservoir and trying to start up from that. And we did two different working fluids just to make sure this is repeatable. It's repeatable. All right, so let me start to talk about some test results here. So first, we did an acetone test with regular startup. So in this case, we charge 10 cc of acetone and helium. I think it's about a certain amount of helium into the condenser. So basically going to the evaporator, just like a regular heat pipe, what we did. And we turn on the heater and trying to capture the startup process. You can see the heat pipe start up around 2,000 seconds and reach the steady state. The figure on top shows the steady state temperature profile, and figure below is the steady state pressure. At steady state, the pressure is around 10 psi. And in this case, no fluid is in the reservoir, so this is considered to be the baseline. So once the heat pipe reaches steady state, we start to do the purge test. So that was done by introduce some working fluid into a reservoir through that field tube directly on the reservoir. So in this case, at 525 seconds, we put like a 0.5 cc of acetone liquid directly into reservoir. So you can see when that happens, you see the temperature delta T between the heat pipe suddenly increase. This is because of the NCG was pushed out and occupying the entire space of condenser. So basically you have off conductance at this situation. And because of the flow, we talk about it, generation inside this VCHP, we are able to remove the vapor in the reservoir very quickly and replenish reservoir with NCG. So you can see the temperature drop very quickly after 100 seconds. We introduced the working fluid into reservoir. And you can see the pressure also dropped very quickly from 14.8 psi back to the original pressure, 10 psi within 180 seconds. And that's how we define the purge rate. So with this purge time, we are able to estimate how fast we can, what is the flow velocity we generated within this VCHP. And we found that the flow is around 1.2 centimeters per second. So like we using the liquid solution showing that if you have maybe 1 or 2 centimeters per second, you can really purge this substance within less than 30 minutes. So, and steady state is the same as a baseline. So after we introduce working fluid, we are still be able to quickly recover back to the normal situation without using any additional heating elements. So after this purge test, we're going to study the extremely startup. So we charge the pipe, but this time we charge all the working fluid, 10 cc of acetone and NCG, not from the regular field tube. We charge all the fluid in the reservoir, and no working fluid was charged in the heat pipe. So obviously, initially when we apply the heat, no working fluid is in the evaporator, so it's not going to operate in the first few minutes. But because of the reservoir is integrated with the evaporator, heat will be able to conduct it to the reservoir and vaporize the working fluid over there. And the vapor will migrate into the condenser, and they will condense and return back to the evaporator through the wick structure. Once you have a fluid in the evaporator, the heat pipe will be able to start up. And once the heat pipe able to start up, the flow will be able to generate it and start to purge the fluid from the reservoir. So at 1,500 seconds, you can see the temperature start to drops and go to the steady state very quickly. Same thing you can see from the pressure. The start up will take like 2,500 seconds. We are able to go back to the normal situations, and the steady state is like the same as the baseline. So we are able to start up in this extreme condition without any working fluid in the evaporator initially. So after we did the acetone test, we start to look into other working fluid just to have a repeatable results. We start trying different working fluid using toluene as a working fluid. This is a baseline. The steady state temperature pressure is about 8 psi. It takes like 2,000 seconds to reach the steady state. And we also did a purge test, introduced a fluid around 200 seconds, recover back very quickly within about 475 seconds. And associated purge flow rate is about 2.1 centimeter per second. And again, the system reached the same steady state as the baseline. And we also do extreme startup test for the toluene. Again, the system able to start up around 2,000 seconds, just like the acetone test results, and the same steady state we have is the baseline. So after we investigated the startup process, next thing we did is we're trying to mitigate the temperature overshoot. So you can see that when we doing this extreme startup, the temperature actually overshoot a little bit to reach about 95 degrees. But the question is, are we able to mitigate that by controlling the heating power? So in this case, we have an on-off heater to control the heater.
You have about 3 minutes left.
Oh, okay, yeah, I'm almost finished. So again, this is extreme stop, and we're trying to regulate the heating using the on-off heater to control the evaporator temperature below 100. In this case, you can see that stop times is slightly longer, instead of 2,000 to 5,000, but the overshoot temperature is much lower. So this is just a trade-off, what kind of temperature you can accept for overshoot, but you will have a longer stop time. So my conclusions for this study is hot reservoir VCHP seems to be a very promising technology for future lunar night survival, lander, rover, or habitats. And but we need to introduce advanced fluid management techniques. And one concept we are developing on the STTR is using this loop configuration to enable purging without using any additional heating. And we demonstrated this concept in phase 1 and phase 2, and the reliability test was completed last quarter. And the result shows that we are able to generate flow with these configurations, and we are able to stop the pipe regardless where your working fluid is initially charged. It can be the reservoir, it can be the evaporator. And the startup time is very similar to the baseline startup time, and the temperature overshoot can be controlled strategically by heating the reservoir on and off, and not the reservoir, by providing the heat to the evaporator on and off. And the takeaway message for this presentation is reliability of this new device is significantly enhanced compared to the regular VCHP with hot reservoir. So I would like to thank the sponsorships from NASA, STTR phase 1 and phase 2 program. Our program manager is Jeff Farmer and Will Johnson. And also I want to thank the technicians working on this project, Bill Texter and Larry Waltman. And thanks for your attention.